scratched the surface on a lot of things and didn't really go as in depth as we did last year.
Part of it's the nature of the course, that you very quickly, when you get it with electricity and magnetism, when you start getting to a greater depth, the complexity builds a lot faster. And so with the mechanics, you get into greater depth and it goes like this. With electricity and magnetism, it goes like this. And so there's a certain limit. We didn't necessarily get into much more depth. Some semesters, we just get to relativity. Some semesters, we get at least 2 days on quantum or 2 days on optics. So now, we did have an extra week, but remember, the classes were 5 minutes shorter, because that makes all the difference.
It's like backup time, I'm pretty sure. The 5 minutes.
Yeah, I'm about to shoot off into a tangent that I shouldn't, so. Don't forget, we're about to go to 7.5 week courses.
Yeah.
I know some teachers who really, the last 5 minutes are very important.
All right, so at this point I was going to do quantum. There's only a certain amount of depth I can get into. I at least want to get to the point where we can talk about walking through walls. That's the hope.
Is that quantum tunneling?
Is
that quantum tunneling?
It is. The electron, yes, quantum tunneling. All right, so last time we touched on it, we at least got to the point where we got to ultraviolet catastrophe, I believe. We did some quantum. Ultraviolet catastrophe, that is, starts with the assumption that the energy of the photon is equal to Boltzmann's constant times the temperature. So the higher the temperature, the greater the energy. And that ultimately led to the situation of the greater the frequency, the closer we get to infinity. And since we are all not dead, we have to assume there was something wrong. So, again, historically, Planck first came up with a function that worked, and then later on rationalized it. And he basically said, suppose the energy is proportional to the frequency. Well, I know that the average energy is equal to, let's do it as a summation to start with. The sum of the energies at a particular state times the probability of being in that state. And although we did not get to it when we did the distribution of how many zero energy states there were, how many zero or energy one states there were, and so forth. If we plotted it, it would have looked something like that. If I did number of states versus energy. And if you kept going with that, you ultimately would see that this, so if we increase the amount of energy, there is a relationship here, and that basically this graph is of the form e to the, whatever your energy value is divided by some constant, which happens to be kBt. So the probability I'm going to be in some particular state, some energy state, is going to be the probability I'm in, that's, or basically what the function equals for that energy. So e to the negative e over kBt, divided by the sum of all the possibilities. Whenever you're doing probability, it's the chance that one thing happens divided by the chance that anything happens. And this is probability of being in sense state I, so I'll just put a little substitute I there. And so therefore, the average energy being in some energy state, which we're saying is proportional to frequency, is going to be, well, the sum of EIPRI, which is the sum of EI over EI times the probability, which is e to the negative EI over KBT, over the sum of if you think about this as a huge sum, we just basically have the same denominator, which I can factor out. And so this just becomes the sum of the energy of that state times e to the negative EI over KBT over the sum of e to the negative capital E sub I over KBT. I'm about to skip some steps, but at least want to set that up. And if EI is proportional to the frequency, or if the energy is proportional to the frequency, then it's going to be equal to some constant, actually two constants I'm going to throw in here. N is just basically the state that we're talking about, first state, second state. H is the proportionality constant. And so if we start with that assumption, we get the sum of NHF e to the negative EI over KBT over the sum of E. Now, and what we end up with in the end is that the average energy is this H times F over E to the negative HF over KBT minus 1. That is the average energy. So therefore, my energy density is going to be the integral, and this is the thing that I did last time. It was the density of states, the 8 pi HF cubed over C cubed, times the average energy, which is HF over E to the negative HF over KBT, minus 1 dF. And if you solve that, you get the curve. So energy density for frequency. All right. Obviously, I skipped a whole lot of math there. So take it on faith for right now. The critical thing here, ultimately, the thing that wins that Nobel Prize for Planck is this assumption that the energy is directly proportional to the frequency for light. Now, there's one bit of experimental evidence besides the black body, which was necessary in order to solidify this, which actually got another Nobel Prize for someone else. So let's talk about what's wrong with everything you've been taught. There were seven major problems with classical physics. One, the black body distribution, which is what we talked about right there. So black body distribution. Planck comes along, solves it. Now, it could just be a mathematical trick. Does this actually work? I mean, the fact that energy is proportional to the frequency, yeah, it works here, but doesn't actually work anywhere else. Problem number 2, the photoelectric effect. Which we'll explore in a little bit more detail in a moment. 3, Compton scattering. Bremsstrahlung. A there. Strahlung. Specific heat. Discrete spectra. And the last one. White note electrons. They'll crash into the nucleus. And those last two get tied together. All right, so let's take you through the little bits and pieces of this photoelectric effect. Starts out with, if I have a metal surface here and I shoot photons at it. Then I have a detector over here, so if any electrons get kicked off, the electrons basically go into the detector. You're, in essence, measuring either moving charge or voltage or whatever the detector has to be set up to do. What they knew was that if light does not eject electrons, then increasing intensity does not eject them also as well. This makes absolutely no sense to think of light, if you think of light as a wave. When you increase intensity of a wave, you're increasing the amplitude. You increase the amount of energy into it. So if I shine a light on it, no electrons are getting being ejected, being basically ripped away from the atoms, then a brighter light should do it if light is a wave. However, if light does eject them, then increasing intensity ejects more. So if a tiny little light can kick an electron off of the atom, then shining a brighter version of that light will eject even more. Einstein takes what Planck had done and combines it with this problem and solves it. So if the energy of light is indeed proportional to the frequency, then shining a light on it is, if it doesn't eject electrons, that means I don't have enough energy because my frequency is not high enough. And if my frequency is not high enough, shining more on it doesn't do it either. That'd be like asking students to touch the ceiling there. If every student is too short to touch the ceiling, bringing more students in, because they're not allowed to get on each other's shoulder, bringing more students in isn't going to make the problem any better. But if you bring in a group of giants, they can touch the ceiling, they'll bring in more in there, more people can touch the ceiling. And so this actually matched what people were seeing. The idea, though, is that light is not behaving like a wave here. So does this mean that Newton was right? Well, we've got to be careful about that. Because if I shine a light at what's called the double slit experiment, or I'm about to do one with multiple slits, but if I shine light at it, if it's a wave, when a wave comes through here, I should see wave basically going through these two slits. And where the light overlaps here, that means I've got constructive interference. Flash back to a semester ago, where I have one peaking and one bottoming out, which would be right here. I have destructive interference. So what I should expect to see is a bright light in the middle, and something not as bright, and something not as bright. That's definitely a wave characteristic there. And we can see that kill the light for a little bit here. I have what's called a diffraction grating. It's more than just two slits. And you can see the multiple points of light. That is called by constructive and destructive interference. I assume you see at least the 3 dots there. I heard a sound to indicate yes there. Yeah. So. And potentially, if we'd done optics, we would have talked about that in more detail. So light definitely is behaving like a wave here, but it's not behaving like a wave here. And so therefore, light sometimes behaves like a wave, sometimes behaves like a particle. Compton scattering, or evidence of particle bit. Compton scattering is I have an electron that's zipping around a nucleus. And by the way, at this point, the nucleus, the concrete evidence for a nucleus existing was probably about 10 years old at best, at most. If I shine light on it, and the electron gets ejected, not only does the electron get ejected, but I have a wave coming off of it like this. That's a different wavelength than what I started with. If energy is proportional to the frequency, that means it's inversely proportional to the wavelength, because wavelength and frequency are inversely proportional. So it comes in with a certain amount of energy, a certain frequency. It ejects the electron, which takes some energy off, and so what's left over is a certain amount of energy, less than what we started with. So it would be a lower frequency or a longer wavelength. You can actually solve through the equation that was found experimentally just using simple treating light as a particle and doing a perfectly elastic collision, two-dimensional perfectly elastic collision.
Classical mechanics still works in some cases.
Yeah, and so that comes into this issue of when can we use it, when can't we? Classically, the average energy was kBT. What they found was, and this eventually becomes one of the axioms of quantum physics, is that if you move it to the classical limit, so you either move it to a large scale or to a slower speed, that any of these equations should come out to be what the classical equation says. And in this case right here, it actually would come out to, and that's one that's a math I skipped, this would come out to kBT as a classical limit if the frequency is small enough. Other questions at this point?
So they haven't found experimentally what frequency you can't use classical mechanics. I feel like that would be something that could be found experimentally.
When you can't?
Yeah, ideal frequency for classical mechanics, and ideal frequency for quantum mechanics.
That cut off. And it's like with relativity. At least I parallel it with that. Yeah, I'm driving home and I'm going to age a little bit slower than my wife who's at home right now. That doesn't mean there's relativistic effects aren't in effect. It's just a matter of, is it significant? And so that's what it really comes down to. At what point is it considered significant? And that really depends on the experiment. So in physics, generally for relativity, special relativity, 10% of the speed of light is generally what has been decided as. Above that, we care about it. Below, we don't care about relativistic speeds. For quantum, generally when you get down to the level of an atom or a photon, then, well, not necessarily with a photon. When you get down to the level of an atom, that's when you start carrying. I don't know if anyone has ever, I don't know what the official, what would be official, what the accepted practice is. Generally, you're working in that realm whether or not. So my dissertation, I was not working in, I didn't care about the quantum. I cared about relativity, but not quantum. Well, actually that's not true either.
Yeah, but if you're working with particles, so it could have had an effect.
Yeah, all right, so let's take it this, we'll get to the point and then I'll try to connect it up with my dissertation.
Yeah.
All right, Brim's problem. Basically, if I take an electron and I zip it towards you and then I stop it before it gets to you, then energy goes somewhere. You can think of it a different way. I have an electron which has a charge moving along and then it stops, which means my electric field will change, which means I create a magnetic field. In essence, I'm creating electromagnetic radiation, more specifically X-rays. And so treating it, again, like a particle, this is another bit of evidence that behaving like a particle will come from that. Specific heat, classical predictions of deriving specific heat, such as how much energy do you need to raise the temperature of an object to a certain amount. Classical physics doesn't really cover that. This stuff does. Discrete spectra, we can actually, yeah, we got time. I cannot project this, you would have to see it. How many of you have seen this discrete spectra before? And you need tubes. Yep. All right, so this is mercury. What I'm going to do is I'm going to put a huge voltage between these two, so I'm going to run current through it. What that does is the current runs through it. I'm basically I have electrons zipping around the nucleus, and when an electron gets zipped by some of that energy, it's going to move to a higher level. It's not enough to eject it, but it is enough to move it to a higher energy level. And then at that point, it's then going to, it's not sustainable, it's going to collapse back down, and when it does, it's going to give off energy. And there's certain gases that give off energy in the visible light spectrum.